Hello, so today we are going to do a presentation on CPU scheduling. We are team 8, and here are our member. There's me, there's Watane, there's Ratisan. So the objective of today is we're going to give a thorough walkthrough on all things CPU scheduling. So we have first come, first serve, shortest job first, shortest remaining time, round robin, and multi-level feedback queue. So our architecture and code. So here we're going to go inside VS Code and check how we implement and run our code. So without further ado, we can just go straight to that. So here's our code. We have the structure here. We have an index where I use this to deploy my code inside GitHub. And then we have specific algorithm. There's 5 here, and the UI to connect those algorithm with this. I would call it the logic. And then I also have a styling. So there's HTML, there's CSS, and then there's JavaScript. So now I'm just going straight to my part, which is first come first serve and the shortest job first. These two are a non-preemptive CPU scheduling algorithm. Wait, here. So it's a non-preemptive algorithm. What does that mean? It means that once it goes inside, it takes the CPU, it does until it finishes the job, and then the next one can come in. So it's not flexible, it's inflexible. It does, the key here is it finishes its job, then the next one can come in. The next process can come in. First come, first serve is simple, is that whenever it arrives first, it does first. It finishes first, and then the next one come in. But it is prone to the convoy effect, meaning that if a long process takes up the CPU, then the shorter process, we have to wait for that longer one, which this is what we call starvation. We're starving the smaller processes. And then there's the shortest job first. This is also a non-preemptive algorithm. Here, it select the process with the shortest burst time, which help minimize the average waiting time. So we can go look into the code first to see the difference. So here, there are buttons such as add process, load simple scenario, clear all, and run simulation. When I click on this, let's imagine I add processes, I add the process, I load that scenario, and then I run the simulation. So it's going to call this function. Currently, we have a process list. So it passes a process list parameter. Then later on, it make a copy into local process. Now it's going to sort the process, which comes first. So here, arrival time minus arrival time A, arrival time minus B, arrival time. What does this mean? It means that, let's say A arrive at 5, B arrive at 2. So if I minus that, that will give me a positive value of 3. So this positive value is saying that the B will be before A. So B first, then A. But imagine if it was, let's say, 7 minus with 9. We're going to get minus 2. So now, in this case, it's going to be A and then B. So that's the sorting process. Then we have here our timeline used for our Gantt chart construction, and current time used for our, as our process move forward, the timeline is going to move forward as well. So the current time will change accordingly. And then here is going to go into each of the process. And this section here I want to mention is that, let's say the process, there's a gap after a process finish, and then there's this idle gap that no process has come in to take the CPU yet. So here this helps prevent that. So when there's idle, there's a gap between one process and another, we're going to push idle. Afterward, once this idle is finished, it's going to go to the next process. And then here if there's no idle, assuming there's no idle, then it's just a simple, it starts when, it ends when, and then the turnaround time, we have a formula, which is completion time minus the arrival time, and then the wait time, we take the turnaround time minus the burst time, response time, we take the start time where the process take up the CPU, and then minus with when it arrived, and then where the idle is gonna be false, and you add the color, put the time inside the Gantt chart, basically. And then it does this over and over in order to draw the Gantt chart, and then here it returns a local process and the timeline. And then we also is going to render this timeline down here, but I will not show that code. Afterward, shortest job first. So for the shortest job first, oh no, not shortest job first, my bad. I was assigned with shortest, yeah, it's shortest job first. So when we click on run simulation, so the big difference in shortest job first and first come first serve is that before for first come first serve, it comes and then it does the process based on the when it arrived. But then here in the shortest job first, it does the process based on the amount of burst time. So the less it is, the first, like, it does the process first. So we can take a look. If we pass in the process list again, and then we're going to put this in local process, we make a copy of it. And here, notice we have simulated process here. Here we want to check whether that process has been simulated or not. So we're doing a loop, a while loop. So if currently completion count is 0, so we have, let's say, 5 process, and then currently the local process will be 5, so 0 is less than 5, then it's true. So if any process has already been simulated, that local process is gonna get reduced. So once it reaches 0, then there's no more process, then it should not run the loop no more. But if there is process, then we're going to loop through that process. And why? Because we want to sort it. We want to sort which process should go first based on the burst time. So here it's similar to the previous first come first serve. So if it's a positive, then B come first. If it's a negative, if it gives a negative, then we sort A first. But then what if it comes, the burst time is the same? So then now we sort based on when it arrived. Okay, that's all. And then once it is sorted, everything is sorted, we know the order, then we can start the simulation. We can start the simulation, we can find the turnaround time, wait time, response time, and then once everything is completed, true, and you push it into the timeline, then you can have return the timeline for us to see the Gantt chart. And now we're going to look into the demonstration. Oh, but no, wait. Before that, I want to give a quick analysis on first come first serve. So here, first come first serve, it's simple, it's straightforward, and it's strictly fair. While shortest job first, this one, it helps make sure that the short process finish first and get out of the queue quickly to prevent small tasks stuck behind larger or bigger ones that takes up longer time to finish with the CPU. So now we can move on to our demo. So I'm going to live demo this. Okay. So I'm going to load my scenario and then I run my simulation. Here, it should be based on arrival time, right? So if we look at the arrival time, it comes in 1, 2, 3, 0, 1, 2, 3. So I expect P1, P2, P3, P4, right? Yes, P1, P2, P3, P4. And then the burst time, you get 0 to 5, and then add 3 more, 5 to 8, add 8, 8 to 16, 16 to 22 at 6. So, and then here, same as the top, completion time, we have the formula for that. No, not the my bad. The completion time is the time here that a process is finished. And then the turnaround time, this is where we have the formula, where we take the completion time minus the arrival time. And then we have the waiting time, we take the turnaround time minus with the burst time. And then we have the response time where the CPU get allocated. So minus it with the, what was it, wait. Minus with the arrival time. And then I have the average of all three by taking like the sum of this column divided by the amount of process we have. And that's all for first come first serve. So next we can move to the shortest job first. I load the process. So here, what do I expect? If I take a look at this, this comes in this order, but I expect this to finish. Then afterward is going to be P2, P2, and then is going to jump to P4 because 6 is less than 8, and then P3. Yes, it's exactly like that. This is a Gantt chart. These are our metric, the same formula, different output. We have a better average waiting time. So that's all for my part. First come, first serve, and shortest job first. So now, if we're going to move on, stick around to find out how interactive environment are performed by the CPU with round robin, and how batch processing environment are minimizing are going to minimize the average waiting time for all jobs with the shortest remaining time presented by my next presenter. Okay, that's all.
Okay, so let's move on to my part, which I will be responsible for SRT and OR. SRT stands for round robin. It's a preemptive algorithms. Preemptive means we share CPU to multiple processes without having to wait for one process to finish first and then let other terminate it. No, we share through multiple process. This is our HTML. There's nothing really important here. It's just to design your web page so it is user friendly and people will be easy and can be understand when they use our SRT algorithms. And we implement all the backend in SRT.js. But before going to that, we have to see the demonstration first. So assume that we have all of this process, P1, P2, P3, and P4. SRT have to check which process has the least burst time or smallest burst time. They will execute it first. But before moving to that, they have to check the arrival time first. Which process come first? So P1 arrive at 0, which means P1 run first. And when time equals to 1, P2 arrive. And then because of P1 already executed one time, this one equals to 4. And then P2 arrive. We compare 3 and 4. Because P2 burst time is smaller than P1 burst time, P2 will be executed. This is just a short explanation. So when we click run SRT simulation, we can see that P1 run only one time, like I said, and then P2 run until it finish, and then P1 run until it finish, and then P4 and then P3 repeatedly. We compute everything into completion tables. We can see that P2 finish at 4, P1 finish at 8, P4 finish at 14. P4 finish at 14 and P3 finish at 22. And then we compute a formula, turnaround time equals to completion time minus arrival times. We get all of this value. For waiting times, we take turnaround time minus burst times. We get all of this value. And then we sum everything together and divide it by the number of process. We get waiting time equals to 5 and turnaround time equals to 10. Okay, that's how the algorithm works. Let's go directly into SRT backend algorithms. So I don't have time to explain everything, so I will just go briefly to which part do something, which part do some things. So first thing first, we have to initialize. This is the default value like you see at the moment. And we put the colors so that each process has different colors. We initialize. This one is we get the element by ID. So when the user click on which button, they will get the element ID from that button, and then we can apply the data algorithm later. This is a function to add a row to the tables. This is to clear a row if we want to remove. Load sample scenario here, if we put our own data and then we want to clear everything, we want to load a sample scenario for easy understanding, we can call this function. Read process from the table here is to read all the process that has arrival times, it names, it burst time, and store it into an array so that we can use it later inside the structure. So this is the main algorithm here. I think it's around here. Yeah, it's only a little bit of code. So this is a function to copy the array from the existing array up there. And then we check the length, we check the constant, we input the time. So instead of starting from 0, it will take the time from the process that have the smallest arrival time first for initialize the first algorithm of SRT. This is to store the value of the process so that we can throw it in Gantt chart. This is the implement algorithm. Like I said, we first thing first, if there's no process, we run based on the arrival time, and then afterwards, if we have more than 2 process coming to the CPU execution, we have to compare which one have the smallest burst time, so we can execute it first before moving to another process. Yeah, it's just to do that algorithms we sort, and then this one is to check whether if they have the same burst time, they will move to one more condition where we have to check which one arrive first, and if not, if they also have the same arrival time, they will move to the one that have the smaller index. We do everything, and then if it is complete, we add complete, so that this is the number of completion process. We store it inside the result, and then this is to calculate for average somethings. So why we need to store this one? We store this so that underneath the algorithms, we can rendering the Gantt chart that you just see at the moment. Then we plot every value into the tables. So this here to render the Gantt chart, we draw the Gantt chart, we take every single things and put it inside this order PID, and then we draw it. And each box has 36 pixels for one process executions. And then this one is to render the value to the tables. When we see all of the Gantt chart, we have a completion times of each processes. We will plot every single value into the table, so that you can see at the moment there's a table with the completion time, turnaround times, and many other more value. And then we can also see the value of the average, which will be calculated inside the algorithm above. So here is a function. When we click a run simulation, we call the function at the top that I just tell you, read the process or some things. And then this is to add even listener. When you click, it's just a design. This one, in short, it's just a design of our HTML file. So let's move on to round robin. Round robin is also a primitive algorithm. So round robin is an algorithm that we have to input time quantums for each process. Time quantums for process to run. And then an easy way to do it is we have a waiting queue for the process that arrive, and put it inside waiting queue, and then it proceed into execution queue, which is related to queue as well. We apply first in first out. So this is an HTML of the round robins. We have all of these things. Like I said, there's nothing really important. This is just the way we design the HTML file so that it is user friendly and user can understand it easily. And we have ID for separated button. It has its own job to do. So before moving to round robin data structure in detail, we have to understand how our website works first. So assume that we have all of this process P1, P2, P3, and P4, and we put the time quantum equals to 2, which means if P1 comes first, P1 will execute 2 burst time, and same goes to other. So here we have a waiting queue because P1 arrived at time 0, which it will be in the wait queue first. So, okay, when we run this one, you will see okay. So basically, P1 proceed 0 to 2, and then P2 comes. When P2 comes, we proceed P2 into the queue. So P2 is here. And then P3 come. P3 is after P2. And then P4 haven't arrived yet. So we check. P1 has 3 more burst time. So P1 will stay after P3. And then we repeat again and again. So after we finish the algorithms, we could see that which one finished first. So P2 finished at 11, P1 finished at 14, P4 finished at 20, and P3 finished at 22. Same formula for waiting time and turnaround times. You just put the formula in there, and then you find the average value, and then you find the turnaround time value. But take note that this one was way longer than SRT. SRT has the shortest waiting times. Okay, just a short explanation. Okay, let's go to this one. So I cannot explain, I have no time to explain all of the code lines. So I will just briefly explain the main logic inside this code. So we have this one is to initialize an array for the process and the time quantum, just to check condition and initialize everything. And then this one goes the same like the SRT algorithms. At the moment, we take the value of each process and then we store it inside an array. Here, it's the same. It's just to initialize everything before we start the algorithms. So like I said, because we are using queue, first in, first out. So whichever come first will stay in a queue, in a waiting queue, and then it will proceed to the execution queue. So one thing you have to notice about this is that after we finish running everything, we have to check which process arrived at that times that the previous process already executed. Like at the moment, P1 execute from 0 to 2, and then from 0 to 2, P2 and P3 arrive. So before taking P1 back down to waiting queue, we have to take P2 and P3 and queue it into the waiting queue first before we finish, before we continue our algorithms. Okay, this is the algorithm that I just tell you. You enqueue the process that arrive first before you drop back the process that still have more much time to execute it. And then after we finish everything, we apply the same method like SRT. We store it inside a completion queue so that we can use it to rendering. And then we calculate waiting time, turnaround time, and response times. See? Yeah, it's nearly the same. This one is to initialize the row, to read the row from something, something, somethings. Same, this is nearly the same to SRT initializations. Read process. And for rendering, it's not that big different at all. For SRT, we don't have a next button, but this one we have next button, which means we can run from step to step to steps. So we get the Gantt array into this variable so that we can use it to plot. So we plot everything into the Gantt chart, and then we replace the part of the Gantt chart in the HTML file with the new things that we implemented. Same goes to this one. This is the function to render queue. We have two queue. We have queue for waiting queue and execution queue. So this is just to create a queue and add an item into the queue itself. This is to render table because after we finish the algorithm execution, we will pass all of the value of a completion time of each process to the table so that we can calculate for turnaround times and waiting times. Okay, here. Same goes this one. We do everything. Oh no, we do everything in here. We write everything like the arrival time, burst time, completion time, turnaround times. We calculate for we take the value of the average and we round up, and then we put it inside the average tables. And yeah, that's pretty much it. This one is just to control the simulation. Because we have existing function on the tops, we could just create a function to start a simulation. So this is to control the simulation. When we click on start simulation, it will run everything, and then we will call all of this function that already exists on the top side. This is a function to do. Next step is if we don't want to run the entire algorithm simulation, we could just click on step by step. So this one is to handle a step by step process. This is stop playing. This one is to just stop at each steps. This is a play all button. Yes, and that is the end of round robins. It's just a quick explanation of the algorithm.
Okay, hello everyone. My name is Raditya and I'm in charge of explaining the CPU scheduling called MLFQ, or this stands for multi-level feedback queue. Okay, so MLFQ is a CPU scheduling algorithm that uses multiple priority queues. It dynamically adjusts the priority of process based on their CPU usage. For example, like short interactive process are given higher priority, while CPU intensive processes are moved to a lower level priority queues. So as you can see, for example here, we have three queues: Q0, Q1, and Q2. Q1 uses round robin with a quantum of 2, and Q1 uses round robin with a quantum of 4, and the Q2 is the final queue where you finish the when you finish running. That's why we're using first come first serve, no quantum. Okay, this is our project structure. We have first come first serve, MLFQ, round robin, SJF, and SRT. Okay, so without any further ado, let's move on to our MLFQ. So we run our code here. Okay, and this is all the CPU scheduling that we have done. And this is mine. Let's get into it. Okay, so we have a process input. This is the process ID. We have P1, P2, P3, and P4. Arrival time was P1 is 0, burst time 5, yeah. P2 arrival time 1, burst time 3. Okay, and then let's move on to our Gantt chart. Let's just click play off. Okay, let's wait for it to run. Okay, so now I will explain to you guys about the Gantt chart of our MLFQ CPU scheduling. Okay, so as we all know, Q0 is the first queue, the highest priority queue, so we run it first with a quantum of 2. Okay, so this is a let's look at this table. We have the burst time of P1 is 5, and then we 5, and then we quantum with quantum of 2. Then 5 minus 2 is 3. Okay, let's remember that P1 now have 3 burst time. P2 we have 3, minus 2 we have 1. We have 1. Okay, P1 has 3 and P2 has 1. And P3 minus 2 we have 6. The remaining is 6, and P4 minus 2 we have 4. And then when you done the everything in the first queue, the Q0, we'll move on to the Q1. Q1 we have the quantum of 4, So as we remember before, P1s have the remaining of 3, so 3 minus 4 is negative, so that means that P1 will complete with time 8. Okay, it will finish at time 10, and then P1 only have 1, so it will finish at 11, time 11. P3 we have 6. Okay, we have 6, so 6 minus 4. The P3 still has 2 remaining. Okay, and this is the time 15. We're at time 15 now, and P4 have 4. That means that 4 minus 4 equal to 0. So P4 will finish at time 19. And when we've done the Q1, the second queue will move on to the last queue. The last queue we are using the first come first serve. Okay, and so all the remaining process are gone except the P3. P3 will still have 2, so just plus this with 2, and we'll get our finish time of P3 at 22 seconds. So this is, as I've said before, the burst time. This is we have this. The completion time of P1 is at 11. So here, as you can see, at 11 P1 will finish, and P2 will finish at 12. Here, finish at 12. P4 will finish at 20. Here at time 20, P4 will finish, and P3 will finish at time 22. Okay, and this is the waiting time. So how do you get a waiting time? For you to get a waiting time, you have to get the turnaround time first. The turnaround time, we will use the completion time. So the completion time here minus the burst time, and you will get the turnaround time. Yeah, and the waiting time here, for you to get it, you have to take the value of turnaround time minus the burst time. Okay, okay, that's it for my explanation of the multi-level feedback queue. Okay, so now that we have finished explaining all the algorithms, let's compare all the algorithm together and analyze each one. Okay, so first come first serve is the simplest algorithm, but a long process run first, then the other process have to wait longer, so it's not convenient. Shortest job first reduces waiting time and turnaround time by running the shortest job first. The shortest remaining time improves on shortest job first by allowing a shorter job to interrupt the current one, making it more responsive than the shortest job first. And round robins give every process a chance to use CPU quickly, so it has a good response time, and it's very suitable for interactive system. And finally, the MLFQ. It's combined different scheduling methods, and it uses aging to prevent starvation, making it the most balanced algorithm overall. Okay, so we will end our project by talking about some of the challenges that we have faced during the development of this simulator. Okay, so one of the biggest challenge was implementing preemption in SRT and MLFQ, since the scheduler has to check which process should run at every clock tick. We solved this by using tick-by-tick simulation. Another challenge was managing the multiple queues in MLFQ. we have to make sure that each process could only be in one queue at a time to avoid bugs. And finally, we implemented aging correctly so that waiting process were promoted fairly without being promoted too often. So overall, this project helped us understand that each CPU scheduling algorithm has its own strengths and weaknesses. First come first serve is simple. SJF and SRT reduce waiting time. Round robin improves response time, and MLFQ provides the best balance by adapting to process behavior while preventing starvation through aging. By building this simulator also gave us a better understanding of how modern operating systems manage CPU scheduling in practice. And that's it for our video. Thank you guys for watching. See ya.